All right, hello everybody. I don't know how well this is going to go, but we're going to give it a shot. I think we're going to talk about the twin paradox today. So, what is the twin paradox? Special relativity is an interesting beast, right? Because all of the equations for it apply to inertial frames, and yet the thing that seems strange about it is that the equations of special relativity are for inertial frames that are reciprocal. So let's imagine that a person is sitting at rest and a person is moving at some rapid velocity and they pass by each other. As they pass by each other, they say hello, and one of them is moving at a relativistic speed but is not accelerating, is just holding steady, right? So, in this picture, Toe Jam is holding steady and Earl is moving very rapidly. Now, they can, at the time that they meet, they can synchronize their clocks, and what they will both see as if they, communicate back and forth with each other, is that even compensating for the travel time of photons from one to the other, they will observe each other's clocks moving slowly. That's a very strange thing, right? Because if that's the case, then you come up with the scenario of, well, let's say that Earl goes out some way and turns around and comes back. And if Earl comes back, they can't both have shorter clocks, right? So what is the solution to this paradox? This is one of the simpler paradoxes that people came up with when they were talking about special relativity. Well, so first off, it's important to remember that special relativity applies, or that the simplest versions of these equations only apply to inertial frames. And so I actually managed to find an article that was written by, I think, Einstein in 1918, which is a dialogue. It's called Dialog about Objections against the Theory of Relativity. I'm not going to read the whole thing because it's fairly long, but I will get to a chunk of it that I think is valuable. I found this at Wikisource, and I'll have the link in the description. So the way that this article is written is it's written as a dialogue between a person, a relativist, a person who is, knowledgeable and, believes the theory of relativity. Of course, this was 1918, where there was not really much experimental evidence for it at this point. And him, this relativist talking to a critic. And so at the start of the article, they kind of go back and forth a little bit about some of the basic concepts of special relativity. And then at some point, the critic brings this out. Now here's the twist. According to the principle of relativity, the whole affair should proceed in the same way if it is represented in a coordinate system K prime that is co-moving with clock U2. He's talking about two clocks that one that's at rest and one that goes away and comes back. Then, relative to K prime, it is clock U1 that is moving to and fro, with clock U2 remaining at rest. It then follows that at the end, U1 should run behind U2 in contradiction with the above result. Surely, even the most devoted followers of the theory will not assert that in the case of the two clocks that have been positioned side by side, each one is running behind the other. The relativist replies, your last assertion is, of course, undisputable. However, the reason that line of argument as a whole is untenable is that according to the special theory of relativity, the coordinate systems K and K prime are by no means equivalent systems. Indeed, this theory asserts only the equivalence of all Galilean unaccelerated coordinate systems, that is, coordinate systems relative to which sufficiently isolated material points move in straight lines and uniformly. K is such a coordinate system, but not the system K prime. That is accelerated from time to time. Therefore, from the result that after the motion to and fro, the clock U2 is running behind U1, no contradiction can be constructed against the principles of the theory. The critic responds, I acknowledge that you have rendered my objection powerless, but I have to say that I feel convicted by your argument rather than convinced. Anyway, my objection immediately arises from its ashes when one bases oneself on the general theory of relativity. For according to this theory, coordinate systems in arbitrary states of motion are qualified. Hence, the proceedings described earlier can equally well be referred to the coordinate system K prime that is continuously connected to U2 as to the system K. The relativist responds, it is certainly correct that from the point of view of the general theory of relativity, we can just as well use coordinate system K prime as coordinate system K. But it is easy to say that the systems K and K prime, in connection with the examined proceedings, stand by no means on equal footing. While the proceedings as seen from system K can be regarded as above, a totally different picture presents itself as seen from K prime, as can be seen from the following comparison. K is the reference frame. Point 1. The clock U2 is accelerated by an external force along the positive x-axis until it has reached velocity v. U1 remains at rest. Point 2. U2 moves with constant velocity v up to point B of the positive x-axis. U1 remains at rest. Point 3. Clock U2 is accelerated by an external force acting in the negative direction of the x-axis until it has reached velocity v in the negative x direction. U1 remains at rest. Point 4. U2 moves with constant velocity in the negative direction of the x-axis until it approaches U1. U1 remains at rest. Point 5. An external force brings clock U2 to rest. However, if we look at it from the K prime reference frame, we get point 1. A gravitational field appears that is directed toward the negative x-axis. Clock U1 is accelerated in freefall until it has reached velocity v. An external force acts upon clock U2, preventing it from being set in motion by the gravitational field. When the clock U1 has reached velocity v, the gravitational field disappears. Now you notice the difference here between point 1 using K as the reference frame versus point 1 with K prime as the reference frame. In K prime as the reference frame's case, we have this gravitational field that appears. And I'm going to spare you the multiple points, but suffice it to say that Einstein argues that this acceleration is very important. He'll continue here. Einstein, the relativist, continues. It should be kept in mind that in the left and in the right section exactly the same proceedings are described. It is just that the description on the left relates to the coordinate system K, and the description on the right relates to the coordinate system K prime. Here he's referring to the left and right drawings under which there's two columns of text that I read from just a moment ago. According to both descriptions, the clock U2 is running a certain amount behind clock U1 at the end of the observed process. When relating to the coordinate system K prime, the behavior explains itself as follows. During the partial processes 2 and 4, the clock U1 going at velocity v runs indeed at a slower pace than the resting clock U2. However, this is more than compensated by a faster pace of U1 during partial process 3. According to the general theory of relativity, a clock will go faster the higher the gravitational potential of the location where it is located. And during partial process 3, U2 happens to be located at a higher gravitational potential than U1. The calculation shows that this speeding ahead constitutes exactly twice as much as the lagging behind during the partial processes 2 and 4. This consideration completely clears up the paradox that you brought up. The critic responds, I do see that you have cleverly pulled away from the noose, but I would be lying if I would declare myself fully satisfied. The stumbling stone has not been removed, it has been relocated. You see, your consideration only shows the connection of the difficulty that was just discussed with another difficulty that has also often been presented. You have solved the paradox by taking the influence on the clocks into account of a gravitational field relative to K prime. But isn't this gravitational field merely fictitious? Its existence is conjured up by a mere choice of coordinate system. Surely, real gravitational fields are brought forth by mass and cannot be made to disappear by a suitable choice of coordinate system. How are we supposed to believe that a merely fictitious field could have such an influence on the pace of a clock? The relativist responds, in the first place, I must point out that the distinction real-unreal is hardly helpful. In relation to K prime, the gravitational field exists as in quotes, in the same sense as any other physical entity that can only be defined with reference to a coordinate system, even though it is not present in relation to the system K. No special peculiarity resides here, as can easily be seen from the following example from classical mechanics. Nobody doubts the reality of kinetic energy. Otherwise, the very reality of energy would have to be denied. But it is clear that the kinetic energy of a body is dependent on the state of motion of the coordinate system. With a suitable choice of the latter, one can arrange for the kinetic energy of the continuous motion of a body to assume a given positive value or the value of 0. In the special case, where all the masses have a velocity in the same direction and of the same magnitude, a suitable choice of coordinate system can adjust the collective kinetic energy to 0. To me, it appears that the analogy is complete. Rather than distinguishing between real and unreal, we want to more clearly distinguish between quantities that are inherent in the physical system as such, parenthesis, independent from the choice of coordinate system, end parenthesis, and quantities that depend on the coordinate system. The next step would be to demand that only quantities of the first kind enter the laws of physics. However, it has been found that this objective cannot be realized in practice, as has already been demonstrated clearly by the development of classical mechanics. One could, for instance, consider, and this has actually been attempted, to enter into the laws of classical mechanics not the coordinates, but instead just the distances between the material points. A priori, one could expect that in this way the goal of the theory of relativity would be reached most easily. The scientific development has, however, not confirmed this expectation. She cannot dispense with the coordinate system, and therefore has to use in the coordinates quantities that cannot be construed as results of definite measurements. According to the general theory of relativity, the four coordinates of the space-time continuum are entirely arbitrary, choosable parameters, devoid of any independent physical meaning. This arbitrariness partially affects also those quantities, field components, that are instrumental in describing the physical reality. Only certain, generally quite complicated expressions that are constructed out of field components and coordinates correspond to coordinate-independent, measurable, that is, real quantities. For example, the component of the gravitational field in a space-time point is still not a quantity that is independent of coordinate choice. Thus, the gravitational field at a certain place does not correspond to something physically real, but in connection with other data it does. Therefore, one can neither say that the gravitational field in a certain place is something real, nor that it is merely fictitious. Now, this goes on for several more pages. I don't want to read the whole thing, but the point that Einstein is at pains to make here is that we have to be very careful what we call equivalent frames of reference in physics. And because we've got a force involved between these two objects, we can't treat them as perfectly equivalent. In fact, they do, as we've seen from his description of those two circumstances, they are different in a physical sense, whether we decide to call that gravitational force real or unreal. It is indeed feeling a force that it cannot in any way tell the difference between that force and a gravitational force. So that kind of solves the paradox in the sense that when two inertial or Galilean frames of reference are moving past each other at a fast rate, we do expect to see this weird reciprocal sense of time dilation, right? However, when one of those frames is actually the subject of some kind of acceleration, things change, and we can no longer use the equations of special relativity to describe the amount of time that has passed on two clocks, one in an inertial frame versus one in a non-inertial frame. If we want to understand how the clock in the non-inertial frame works, we need to work from the inertial frame, and only then can we use the equations of special relativity in their simplest form to come to the answer. I'll actually show here for a moment. Over on Wikipedia, there is an example of how to do the mathematical calculations to determine the differences in coordinate versus proper time, or in inertial versus proper time, from the perspective of the spaceship that is, accelerating away and then accelerating back toward. You'll see that those equations look a little bit more complicated to deal with than the simplest stuff that we're going to see in special relativity. So now that we've kind of understood what's going on with this paradox here and why it isn't really a paradox, now what we're going to do is we're going to look at the actual equations that we use from special relativity to determine what's going on here and see what kind of numbers we actually expect to see here. So, there's also one other little thing that I wanted to mention that I thought was fun, and that's when I was looking this up. Some of the descriptions I was reading were talking about using an ideal clock, I think is the phrase they used. And an ideal clock is a clock that is not affected by accelerations. And you might say to yourself, depending on how old you are, well, a clock that's affected by acceleration, that seems like a really stupid thing. Why would anyone have a clock that's affected by accelerations? But, of course, if you've ever, and of course most of you see where I'm going with this, but if you've ever used seen a grandfather clock with its long pendulum, in physics, you can determine for an ideal pendulum the period of that pendulum, and indeed it is dependent on the acceleration of gravity in this case. And so for a stationary pendulum clock with a force of gravity applied to it, the frequency, the angular frequency, is the square root of g, the acceleration of gravity, divided by the length of the pendulum. Now that has a few assumptions in it, and some of those assumptions are why grandfather clocks are built the way that they are. You might say, well, maybe having the long L makes it so that you have a shorter period, and so you can measure times more accurately. And actually, there might be an element of that, but actually the element that makes longer grandfather clocks better is that in order to come to this very simple expression for the frequency of a pendulum clock, you have to assume that sine of theta, sine of an angle, is equal to that angle in radians. And that is true roughly only for very, very small values of an angle. And so having a very long pendulum actually makes the angle that it subtends as it swings back and forth smaller, which helps to make that approximation closer to correct. If you think about the classic pendulum clock, it has a very long pendulum, very thin, lightweight thing connecting to a circular weight at the end of the pendulum. Well, that's because you really need to have a point mass at the end of the pendulum, and you really need to have zero mass of the stick itself. Any mass that's part of the pendulum, that is the extension of the pendulum, will move the center of mass of the pendulum system a little bit upward, and will make it so that you have to correct for that. And so the lighter you can make that stick, and the heavier you can make that thing, and making it round means that it has no rotational variation as it moves over that little angle as well. Anyway, I just thought that was a neat little tidbit, because I was like, because I haven't seen a grandfather clock in a long time, and I was like, well, wait a minute, why would someone build a clock? Oh, right. Kind of one of those things. Anyway, so let's get actually to the math itself. So what I'm going to show on the screen here is the equation for the proper time of a clock that is in motion relative to another clock. So the proper time tau over there on the left is equal to the square root of 1 minus velocity squared over c squared, end of the square root, times the time of the stationary clock, or of the clock that's moving at that velocity. This is reciprocal in inertial frames, so it doesn't matter which is which in that case. In our case, tau is going to represent the time that passes on the clock that is on the spaceship, and t is going to represent the time that passes for the clock that is in an inertial frame the whole time. So moving forward, we can do a little bit of algebra. We can say that t over tau is equal to this square root expression, right? And right now, v is still a constant, right? We're still working in two inertial frames. V is not a function of anything. It's simply a constant. So we now have this case for the constant velocity. But what we can do is we can bring the interval that we're looking at to a very small value. And so you'll see in this next equation, we have a differential expression. d tau over dt, that is the derivative of tau with respect to t, is equal to this thing where v is now a function of t, or at least it could be. It could be constant, this would still work, but now we're dealing with a very, very small infinitesimal period of time where we're measuring the velocity at that time, and we're taking that all the way to the limit where that infinitesimal bit is basically nothing. Basically so that we can turn it into an integral, because that's what we're going to do next. We're going to integrate both sides with respect to t. We can, if we do that on the left side, we basically just go from having d tau over dt to just tau, from one point in t to another point in t. But on the other side, we now have an integral of this square root nonsense with respect to dt, and v is a function of t. So we're going to have to look at this more carefully. Now, again, like I said, we're going to have to operate from the perspective of the stationary, of the inertial clock. And so we're looking at v as a function of t, and we're going to give it a form like this, we're going to assume that the spaceship is capable of some kind of constant amount of acceleration. We're going to say 10 meters per second squared, which is about equivalent to 1g, a little bit more than that. Just to keep the numbers simple, right? At least simple until we start square rooting things. So the velocity at time t that the inertial observer will observe is going to be equal to a times t divided by the square root of 1 plus quantity, at over c, that quantity being squared. This is another classic, basic special relativity equation, and as long as we are looking at it from the perspective of this stationary or inertial frame, it should work, right? So now we can kind of plug this expression for v into our integral from the previous equation, and we get something that looks like this. Tau is equal to the integral from t0 to t1 of this big old quantity here. This looks complicated and it looks kind of messy, and it in fact is, but it's not too hard to deal with, we're going to find, okay? Because what we're going to do is we're going to start with a change of variables. We're going to define a variable c. Every physicist's favorite. No one else is using this Greek letter, which is equal to acceleration times time over c. Then we come to we can calculate that dt from our integral is equal to c over a times dc, and that t1 is equal to a over c times, or rather that the integral limit of t1 goes from a over c times t1. T sub 0 is going to be 0 in any case. So then we end up with an equation that looks like this. Tau is equal to this messy integral. But this integral still isn't too bad. We can do a little bit of algebra on that integrand by itself. By the way, before I get too ahead of myself, what I'm going to do is I'm going to show on screen an image of what this integrand looks like as our acceleration happens, basically. So I've taken a plot, I've made a plot that shows how our integrand, I'm not doing the integral yet, I'm just looking at the integrand, how that moves as a function of t as we accelerate. So what you're going to see on this integrand is that it starts at 1, as we would expect, right? If they didn't move at all with respect to each other, then tau and t would just be equal. Those two clocks next to each other would just continue to turn at exactly the same rate because there's no velocity between them. They're both in inertial frames. They're right next to each other. They can just, it's just like you would expect to do, in normal life. And so if we took this, if we did that, we would have an integrand where the integrand just stays 1 for all time. If the two things were motionless with each other, if a was 0, right? And so what we would get is, you see the dotted line, kind of the light red dotted line over the top. That's what our integrand would look like in the case of no acceleration. Now what I've done is I've said set our acceleration to 10 meters per second squared, and set our t1, the amount of time that we're going to allow this thing to accelerate, to 1 times 10 to the 9, or 1 times 10 to the 8 seconds. Now, I chose these values deliberately, because what you'll note is that in a Newtonian perspective, a times t would be the velocity that you get after time t. And in fact, if we were in a Newtonian system, right, then 10 times 1 times 10 to the 8 is equal to 1 times 10 to the 9, which is greater than the velocity of light. That's why we have this equation to kind of knock the velocity down a little bit for the sake of relativity. So with that said, we're going to plug that velocity equation back into our integral, and the integrand looks like what you're going to see on the screen now, or what we've been seeing on the screen, basically. It starts at 1 because the velocity is 0 at t equals 0. Then it gradually curls down, and then what you're going to notice is that it doesn't keep curling down; it levels off. And the leveling off is the fact that this acceleration is going to start to have less and less of an effect on the perceived velocity of the spaceship as it gets faster and faster and faster, right? It takes more acceleration to get yourself to increase your velocity, from the perspective of that inertial frame, as you get closer and closer to the speed of light. In fact, we're going to discover that if we let the acceleration proceed this way, that our final velocity in the frame of the inertial frame is actually about 0.957 or 958 times the speed of light. We're not quite there, but we're pretty close. Anyway, back to the integral. So we've done our change of variables. The thing still looks a little kind of a little bit gross. You know, C and A are constant, so they can go outside the integral. But let's take a look at this integrand without the factors. And can we do something with it algebraically? In fact, it turns out that we can. We have this big square root, 1 minus c squared over 1 plus c squared, right? Well, we can take that 1 and we can turn it into 1 plus c squared over 1 plus c squared, and then subtract the c squared minus, or c squared over 1 plus c squared. And because they have the same denominator, we can just subtract them. And we get 1 over 1 plus c squared. And we take the square root of that whole thing. Now we've simplified our integral to something that looks like this. Tau is equal to c over a times the integral over this interval of the square root of quantity 1 over 1 plus c squared times dc. Well, it turns out it's not like we couldn't do this. It's not like we couldn't do this ourselves with some tricks, but it turns out that this is actually one of those standard integrals that you can just kind of look up. And I've got my table of integrals book, and it turns out that this is equivalent to that this integral is equivalent to the inverse function of the hyperbolic sine of c, and then we take that from the range of 0 to a over c times t1, which is just going to be, you know, which is just going to be 10 times 10 to the 8 over c. All right, the thing that so now that we've got our integral, we calculate it. What I'm going to show you next is actually a visual aid. Now remember, each of these we're going to split the whole trip into 4 parts. The first part is where the accelerating twin is accelerating away from home. Then he begins to decelerate by pushing in the opposite direction the same amount. And then he continues, then he reaches a point where he is stationary with respect to the inertial frame of home. And then he continues accelerating, this is stage 3, in the direction of home until he reaches that same value of velocity again. And then he decelerates again for the same amount of time. Because now you could come up with weird like functional forms for the acceleration for each of those cases, but what I'm going to do is I'm going to do it basically pictorially here. We see that from our first stage, we're going to be basically accelerating from a velocity of 0 to this maximum velocity, which is about 0.958 times c. We're going to be accelerating, you know, in the local frame of the acceleration, we're going to be accelerating constantly. And we're going to see that the integrand looks like this. And so the integral of this integrand is the area under this curve, right? But, and so if we were going to do the integral by hand for the other 3 parts of this, what we would have to do is we have to come up with functional forms for the acceleration, for the velocity as a function of time in these later areas. But what we can actually do is that since we've split this thing into 4 equal parts, we can simply take, and we know that we're going to be going from a velocity of 0 to a velocity of this particularly high velocity, you know, over and over again with the same acceleration. We can simply take the integrand, we can simply take our picture of the integrand for the first quarter of the journey, flip it over on horizontally, and paste it on for the second quarter of the journey. We now have gone from a velocity of 0 to a high velocity, back to a velocity of 0, and then once again we can go from a velocity of 0 to a high velocity and back to a velocity of 0 and arrive at home. Basically, the result that we're going to get from the twin that left and came back is that the amount of time that passed for him is going to be 4 times c over a, right? Speed of light over the acceleration, 10 meters per second, times the inverse hyperbolic sine function of the value of c from 0, which is fine, that's 0, to a over c times the time, or rather it'd be 1e9 over c. And if we go through and we calculate this out, what we observe is something very interesting. What we observe when we do these calculations is we find out that the clock that has not moved, the clock that is inertial the whole time, has ticked out 4 times 10 to the 8 seconds. That corresponds to 4,630 days approximately, or approximately 12.675 years, using 365.25 for the number of days in a year to deal with leap years. Sure, fair enough. So it's been a little over 12 and a half years for the stationary twin. He has aged from, say, 20 to 32 and a half. The twin that has left and come back only experiences a time, an elapsed time of 2.3 times 10 to the 8 seconds, 2.3019, etc., 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 which is only equivalent to 7.29 or say 7.3 years approximately. Again, using the same, leap year approximation. That means that the twin who stayed at home is about 12 and a half years older once this whole process is done, and the twin who left and came back is less than 7.5 years older. That is a pretty interesting, to me that's a very interesting result. And now that we understand that we can't use the simple special relativity calculations from the perspective of the moving twin, but we have to use it from the perspective of the inertial twin, we now understand that this doesn't go both ways, that there's no paradox here. But this is a cool result. The twin that left and came back has aged a little more than half as much as the twin who stayed home. I just think that's kind of fun. We put some real numbers in. They're realistic. We're accelerating at about the speed of gravity, or at about the acceleration of gravity. We're doing so for, I guess, about 3 years. Accelerating at gravity for 3 years, then decelerating for 3 more years, then accelerating in the opposite direction for 3 more years, and then decelerating for 3 more years. We end up with this very simple expression that tells us that, yes, indeed, there's a pretty significant difference if you were able to accelerate that way for 3 years. So, conclusions. The twin paradox is perhaps only the simplest paradox, or apparent paradox, that appears from general relativity, or from special relativity. As I was doing research for this particular calculation, I stumbled on 2 more of them. One of them is called the Spaceship paradox. It's the connected spaceship paradox. And then another one is an Ehrenfest paradox, I believe is what it's called. I'm going to put links to both of those in the description so you can continue following down this rabbit hole if you feel like it. I'll post a link to the wiki source article, which is the translation of that 1918 paper by Einstein, so that you can take a look at more of that if you like. And it's worth noting that as I showed, the equations to deal with things from a general relativity perspective are a little bit more difficult, but they're not impossible, right? The fact that GPS, Global Positioning System, works as well as it does is because all of the math for this general relativity stuff is pretty well known. And of course, you have to remember that none of us right now are actually in a perfectly inertial frame. We're on the surface of an orb that's spinning around the sun, and there's all kinds of goofy accelerations that are happening. They're pretty small, right? Like things appear inertial from our perspective. But if you start, for instance, shooting a cannon that goes miles and miles and miles, you have to compensate for the Coriolis effect. There's centripetal forces and things like that. The difference between a spring tide and a neap tide is due to the additional or restraining gravitation from the sun, I believe. So these effects are noticeable, in certain places here on Earth, and it's worth kind of trying to understand them as well as possible, and that's why I kind of ended up becoming a physicist. Anyway, that's all I've got for today. Hopefully this video was a little bit, hopefully this video was understandable. You know, if you need to slow down and look at the equations, spend some more time on them, you might want to do that. I tried to show the steps. It's hard to show steps in algebra, but if I can show, you know, what's being converted into what, and then say here's this and here's that, hopefully you know, you can work through that if you want. But you know, I think that the most important thing was this Wikisource article from Einstein, where he kind of goes into depth about why some things that appear to be paradoxes are in fact not. So, that's all I've got for today. As always, thanks for watching. Thanks for listening. If you like what you see, if you like how this channel's going, you know what to do. And I will see you all tomorrow for my Ultima 7 video. Hopefully it'll be a little bit less intense and more fun. We'll see. Have a good one.